Good evening, Vitali. My name's Andrew. I received an email from Rick. He had asked me to help you out with some questions you had, so I'm going to try my very best to answer these questions, and you can hopefully use this to get to where you need to be. Okay. So I'm just going to refer to the questions as you have them labeled in the email. So question 11. No, not with the highlighter though, eh? Try this. Question 11. Okay, so question 11 says, a 4160 three-phase 400 horsepower motor draws 75 amps at a 0.7 power factor. The motor will be corrected to unity power factor with a capacitor connected in parallel with the motor terminals. Calculate a new line current drawn by the motor and the capacitor. Okay, so before we can start this question, we have to first figure out what our original motor was operating at. So I'll represent the values of the motor on a triangle, okay? So my triangle is going to represent three things. It's going to represent the line current of the motor originally, which was 75 amps. Okay, and it's also going to represent my power factor, 0.7. I take that 0.7 and I use the inverse cos. So cos 0.7 should give you an angle of 45.5 degrees. That 45 degrees is the relationship between the VA and the power, or in this case, the line current and the in-phase component of current. So if I go 75 amps multiplied by my power factor of 0.7, I should get a number relatively close to 52.568 amps. Perfect. So that's my in phase, or my IR, resistive portion of current. Now I need to find my reactive portion of current. So there's a couple ways I can do that. I can use trigonometry, or I can use Pythagoras' theorem. So I can go 75 squared minus 52.568 squared, and that should equal a value of approximately 53.493 amps. Sorry, 493. Okay, fantastic. So these are my motor values. Motor before power factor correction. Okay, excellent. Hopefully you understand that capacitors provide a counteractive power to inductive VARs. Okay, so if I was to look at this, what we do when we power factor correct, Vitali, is we correct for the out of phase component of current. So now I'm going to draw my new circuit, and they told me it was going to operate at unity power factor. When something operates at unity, it has a power factor of 1. So that tells me that all of the input is what I'm getting out as output. So I bring this value across to here, 52.568 amps. Because I've now installed a capacitor that will correct It will now provide all of the energy for the out-of-phase component. So these two values effectively cancel each other out. So what am I left with? 52.568 amps. Okay, so the answer they should be looking for in that question is somewhere relatively close to 52.568 amps. All right, on to question 12. Okay, question 12. A 208 three-phase 100 horsepower motor has a power factor of 0.7 and is required to be corrected to a power factor of 0.95 with a capacitor bank connected in parallel with the motor terminals. Calculate the kVAR of the capacitor bank to perform this correction. So once again, just like the previous one, we'll start off with our original motor. Originally, our motor had a power factor of 0.7. Again, I'll use that 0.7 to calculate for the angle. So inverse cos. Give it a little bit more room here. Inverse cos 0.7 should give you, once again, 45.5 degrees. Write that down. Not 44 though. 45. Perfect. Now, they told me it was a 100 horsepower motor. I can take my 100 horsepower, multiply it by my demand of 746 watts, and it'll give me a total wattage of 74,600 watts. 74600 watts. So that's my in-phase component of power. Can I find my VA now? Yes. I can go 746 74,600 watts divided by my power factor of 0.7 should give me 106,571.429 VA. Excellent. Represented on the hypotenuse of my triangle. Perfect. Use Pythagoras's theorem to solve for this side of your triangle, and you should get a value close to 76,012.119 VARs. Okay, so now we have all of the values for our motor. Once again, this is our motor. This isn't our circuit, this is our motor. Okay, motor. Come over to get myself a little more space here. Now I'll draw a new circuit triangle. I can bring my watts across. New power factor. They gave me a new power factor of 0.95. You should be able to once again use inverse cos to change that to an angle. Can I find the new VA? Whoop, sorry about that. Can I find the new VA? I definitely can. Give myself a little bit more room next time. Sorry about that. Should give you 78,526.315 VA. Perfect. 78,526.315 VA. Okay, I can bring my VARs. So sorry, I should have labeled that XL to represent my motor. Bring that across. 76,012.119 VARs of my motor. XL. Can I use Pythagorean theorem to find my total VARs? I can. So I would go X total would equal the square root of 78,526.315 squared minus 74600 squared. And you should get an X total of somewhere in the neighborhood of 24,396.275 for X total. Now I need to find the VARs of the capacitor bank, so XC. Okay, the difference between XL and X total will give you your XC. Well, let's write that in a different color pen so you can follow. XC equals 76,012.119 XL minus 24396.275 X total. XC should equal 51,615.369 VARs. Okay, don't worry if your numbers are a little off from mine, as long as you end up with a total 51.6 K VARs. That should be the answer. Well, that doesn't work very good. I should have highlighted that in a different color. Sorry. And there you go. There's your answer. Give it a nice yellow highlighter. Can't go wrong. All right. Question number 1. Okay, I have a capacitor bank that has a 14 kVAR rating operating at 480 volts. They want a R90 conductor, I'm assuming copper, and the equipment is terminated at 90 degrees. So what have I got to do first? First I need to find I line. I line would be equal to the VA of the capacitor bank divided by E line times root 3. Okay, I line would equal a VA 14,000 VA divided by your 480 volt times root 3. I line should be equal to 16.9 amps. I then go to the code, the CEC Rule 26-208, Subrule 1, which states the ampacity of a capacitor feeder circuit and branch circuits shall not be less than 135% of the rated current of the capacitor. This capacitor bank has a rated current of 16.9. I will now apply the demand factors applicable by the code. 16.9 amps multiplied by 1.35 should give me a value of 22.8 amps. I will then go to table 2, 90-degree column, and I would select a number 12, copper conductor, which is good for 30 amps at 90 degrees. Perfect. Now on to the last one, question 22. A single 5 kVAR capacitor is used to correct the power factor on a single phase high intensity discharge lighting circuit. The supply is 480. The minimum ampacity of the conductors feeding the capacitor is... Okay, so what do? We've got to find I line. I line in this case will be equal to the VA, so 5,000 VA divided by the voltage, which is 480 volt. I line should be equal to 14.06 amps, and that is my minimum ampacity. Okay, that minimum ampacity then needs to have the demand factors applied to it from 26-208. I would take the minimum ampacity of 14.06 multiplied by 1.35, or 135%, will give me a value of 18.98 amps. And that should be the answer for that one. Hopefully I've provided the types of answers you were looking for, Vitaly. Feel free to send me another email if you have any more questions. Thank you.